to. Okay, let's we study about the dynamic model of level in a storage tank, or until we get the transfer function of the level system. Okay, so consider we have a tank with the volumetric flow rate input is Qi and volumetric flow rate output is Q, and at steady state condition it has Higgs height. The height of the level is Higgs. So this one is volumetric flow rate input. Volumetric means that the unit is a volume over time. For example, so this one volume over time, the unit, and Q is volumetric flow rate of output stream, and the unit is the same. So how to get the differential equation on the dynamic model of this system? We can apply the mass balance here. So the mass balance, from the mass balance, so mass balance is accumulation is equal to input minus output. Mass at accumulation, or accumulation mass, is equal to mass input minus mass output. Okay, the mass input here, mass input is volumetric flow rate Qi time rho, because we have the correlation. Rho is mass over volume, then mass is volume time rho. So if we have volumetric flow rate time rho, volumetric flow rate time rho means mass flow rate. So now we have mass flow rate here. So from the volumetric flow rate we convert to mass flow rate, and mass output in the similar method, Q time rho. And what the accumulation? Mass accumulation. Yeah. So the mass in accumulation is volume time rho, or rho time volume. And now the volume of the tank, the volume of the tank here is volume is A time Higgs. So rho, the mass accumulation, rho time A time Higgs. We assume that rho is always constant, then we can get the equation like this. Okay, so the complete equation is accumulation is rho A Higgs, the input is rho Qi, and the output is rho Q. And for the rho constant, so the rho constant, then we can cancel out the rho from this equation. Okay, now we have an equation like this, but remember that the dynamic behavior Higgs always change every time. Then Higgs is a derivative form. So rho a dH over dt is equal to Qi minus Q. Okay, Q is volumetric flow rate of output, can be found by this Bernoulli principle. If there is only natural force, mean that potential and energy force only, there is no pump here, then we can find the Q. What is the Q? So from the Bernoulli equation, if Bernoulli equation is P1 over rho plus V velocity 1 square over 2 plus G Higgs 1 is equal to P2 over rho plus V2 square over 2 plus G Higgs 2. Yeah. 1 and 2 is a point 1, but in this case is 0.1 here and 0.2 here. Okay, so in this case P1 is equal to P2, that is 1 atmospheric, and the velocity 1 we assume very small, so the velocity 0.1 is very small, so we assume 0. Then we can cancel this equation. P1 is equal to P2 and V1 is 0. From this equation we get that V2 square over 2 is Higgs 1 minus Higgs 2 times G. Okay, or V is square root of G 2 G Higgs 1 minus Higgs 2. Higgs 1 minus Higgs 2 is Higgs of the level, so V2 is 2 G Higgs. Yeah. Okay, so what the Q now? Q is the velocity 2 times the cross-sectional area of the hole. So Q is V2 times A. So in our case, for example, here when the area is A, then the Q, the volumetric flow rate will be velocity times A. So now we get the A times square root of 2 G Higgs, A times square root of 2G square root of Higgs, or A and times square root of 2G is a constant, mean G is CV times square root of Higgs. CV is a constant that the value depend on the opening of the valve. So here CV is constant depend on opening of the valve. Okay, now we get the complete differential equation. A dx over dt is equal to qi minus sorry minus cv square root of h. This is non-linear differential equation because the h mean the dependent variable is a power of a half or not one. So this type of differential equation is nonlinear differential equation. But one method to solve the differential equation is using Laplace transform. Laplace transform. But Laplace transform can solve nonlinear differential equation. So for nonlinear differential equation should be linearized. To solve differential equation using Laplace transform, the requirement is the differential equation should be linear. So we have to linearize the nonlinear differential equation. Linearize first, and then we can solve using Laplace transform. From the Laplace transform, we can inverse Laplace transform to get the time domain again. So Laplace transform use the S domain, and then we can convert to time domain again using the inverse Laplace transform. And then for final result we will get the ht, mean the h value every t. So if we replace the t by the time 0, 1, 2 or 0, 0 0.1, 0 0.2 until a certain number, then time, then we get the response of the ht to time. Okay, sorry, I have a mistake for this symbol CV, constant of the valve. Okay, because of some differential equation is nonlinear differential equation, and to solve the differential equation using Laplace transform should be linear. So now we study the linearization of the nonlinear differential equation using Taylor series. So linearization using Taylor series. Okay, so the fundamental of linearization is the condition of nonlinear equation can be assumed linear in the nominal steady state operating point. Nominal steady state operating point. So in the nominal steady state operating point, we assume that nonlinear response is linear. So just imagine, for example, the nonlinear uh, response like this, and we assume in this point, so any point here, so we assume that for the small ring, the small ring is linear. The small ring of the response is linear. Okay, so here is linear. Also this one we assume, or we approximate linear response or linear graph. So in this differential equation, nonlinear differential equation, we assume linear in the nominal steady state operating point. So the definition is the definition of Taylor series method. If we have dy over dt is a function of y and u, y is output, dependent variable, and u is input, independent variable, can be approximate. So dy dt can be approximated by a function of y and u, function of y and u at steady state. So the value of the equation at steady state plus differential of this equation respect to y at y and u at steady state time y minus y steady state. Y minus y steady state means the deviation variable is the deviation between current value and steady state value, and plus differential of function respect to u at steady state, y bar and u bar, time u minus u steady state. Okay, so by definition, at steady state, the value of the function is 0. So we define that at steady state the value of this function is 0. So this one is 0. Then we can write that dy over dt is df over du this part plus this part. So if we define df over dy at y and u is df over dy s, mean at steady state, and y prime is y minus y bar, y current minus y steady state, and u prime is u minus u bar, then we get that dy prime over dt is df dy at steady state time y prime plus df over dy at steady state time u prime. Okay, so maybe you still have a question why we define at steady state is 0, because the deviation at steady state is 0, no deviation at steady state, because uh, no deviation at steady state condition. Okay, and then why we change from y with y prime here. Y prime is y minus y steady state, because actually this is the y current minus y steady state here, but y at function of the value of this function is 0, so I didn't write on. But for the last Taylor series method to linearize the nonlinear differential equation can be simplified using this equation. Okay, now an example of linearization of Taylor series. Linearization using Taylor series method. So as we have a dynamic equation of level storage time, that is a dx over dt equal to qi minus cv square root of h. Okay, so from definition of Taylor series, we have dy over dt, mean the here the y is h in our case, and u is the input or independent variable is qi, and the dependent variable is h or y. So y is output or independent variable, u is input or independent variable. So h is dependent variable, and y prime is h minus h bar, u prime is u minus u bar. Okay, sorry, in our case here y prime is y minus y bar, so we can convert this our problem to the general form from the Taylor series. So dy dt, we get qi over a, h is y, dy over dt is equal to qi over a minus cv over a square root of h. This is our dy over dt. Okay, and then there are two parts of the Taylor series, that is dy and du. So now we get the df over dy first, as is our df, our f is this one. So from dt over dy over dt is function of y and u, so this is function y and u. So sorry, this one function y and u. So we have the differential equation function y and u, and then we derive this equation respect to y at steady state. Okay, so differential equation of u over a cv over a square root of y respect to the y and at steady state. Okay, so what the differential of u over a respect to y? The differential is 0 because no y term here, no y variable here, and this part cv over a is constant, and we have the y variable here, mean that actually this is the y power a half. So you can derive the derivation of this one cv over a time a half. You done the a half y bar half, so a half minus 1, a half minus 1 is minus a half. So the derivation of f respect to y at steady state mean at y and u steady, y and u steady. Now we get minus cv over a times 2 times square root of y bar. So remember y bar because at steady state. And the second part, t f respect to du, the derivative of f respect to u at steady state mean that the derivative of this equation cva y the power half du at steady state is the derivative of u over a is respect to u is 1 over a, because we have u with power is 1, and the second part there is no variable u, then minus 0, so we have the differential f respect to u at steady state is 1 over a. So from our definition of Taylor series, that dy prime over dt is equal to df over dy at steady state y prime plus df over du at steady state u prime. Now we have derived the value of the f over dy is here, and df over du at steady state is here. Then now we get that dy prime dt is 1 over a u prime minus cv over 2a square root of y bar times y prime. Okay, so this is the final result of our linear differential equation. So we got the linear from non-linear here, non-linear differential equation. After Taylor series method, we get linear differential equation. Okay, so this is the example of linearization. Example of linearization of non-linear differential equation. Okay, maybe you want to convert again or replace again y by h and u with a qi. So for the final, if you want to get the final h in variable h and q, so dh dt is equal to qi prime minus cv 2 over 2a. Okay, so sorry, this a. I want to put the a to the left side. Okay, so square root of y bar times y prime, a and a we can remove to the left side. Okay, so this is the linear differential equation of our case. Sorry, so this y is h. Y we have replaced by h. Okay, now we can summarize that after linearization, our nonlinear differential can be converted to linear differential equation dh prime dt minus q is equal to qi prime minus cv over 2 square root of h prime h prime square root of h. Sorry, so after linearization, now we get the h prime, mean that now we have the linear because the degree here is 1. Okay, remember that this part is constant because the square root of h bar mean at steady state we have the value, then we can define this part cv over 2 square root of h is a constant, is constant, and for later study we define as 1 over r. R is resistance of the valve, so R is resistance of the valve. So if we have a system like this with R, mean that the R is Cv over 2 square root of Higgs bar. So R is resistance. The flow from the tank to output stream, there is a resistance here. So for the common on the simplified equation, the perfect equation can be write by Higgs prime over R. That's the more simple equation. Okay, just want to highlight here that the original equation here, dH over dt without prime, but after linearization we have dH over dt with prime symbol, mean that the prime symbol is Higgs minus Higgs bar, is deviation variable. So the deviation variable near the steady state value as a base value. Okay, when we got the linear differential equation, we can solve using Laplace transform. Okay, the Laplace transform of a dx prime dt R is a, so the Laplace dx over dt is s times Higgs s minus Higgs prime 0 is equal to QIS. So the Laplace transform of QI is QIS, and the Laplace transform of Higgs is Higgs s over R. So why we write this equation? Because any variable that may vary, mean the dependent or independent variable, we convert from time domain to Laplace domain. So Higgs we convert to Higgs s, QI QIS. The Laplace transform of Higgs is Higgs s, but R is constant. It's always constant every time. Also A always constant. So we no need to get the Laplace transform here. Okay, so again in this form we have Higgs prime 0. Higgs prime 0 means Higgs value at time 0. At time 0 Higgs, so at time 0 Higgs is equal to Higgs steady. So Higgs prime at 0 Higgs steady minus Higgs steady, mean we get the 0. So here is 0. Okay, and then we get the A A time S Higgs S is QIS minus Higgs S over R, or I remove the Higgs S to the left side, then we have here Higgs S AS plus 1 over R is equal to QIS. Okay, now we have the Laplace transform like this, so we can simplify to Higgs S over QIS is 1 over AS plus 1 over 1 over R. So this is the input. Higgs is Higgs S is output, QI is input, mean that output over input is our Laplace transform. Here is, we call it as transfer function. So this is the transfer function of our system. So transfer function is the Laplace transform of output over input. So Laplace transform of output over input. This transfer function can be converted to the general form. So if we multiply by R over R, mean we multiply by 1, so the value should be the same, all in the same. So this form can be write as ARS plus 1. Okay, so for the general form of first order, general form of first order system, transfer function GS is K over tau S plus 1. So in our case, the K is R, or the tau is AR for the level system. So our first order system, our case, the level system, we get the first order transfer function. So Higgs S over QIS is K over tau S plus 1. So this is the first transfer equation. Okay, now how to find the Higgs T, mean the response of the level, if we introduce an input to the to the system. So if we throw in a block of transfer function, we get the K over tau S plus 1. This is our output Higgs S, and this is our input. Okay. So this Higgs S over QIS here can be thrown in a block like this. So output is transfer function time input. Output is transfer function time input. Okay, so what the Higgs T if we introduce the input here, Q I T For an example, we introduce an input is step, so with the magnitude m here. What the Higgs t? So we can find the Higgs t using the inverse Laplace transform. So Higgs s is transfer function tau s time input. For the step here, the Laplace transform of step is m over s. So here u t is m, then u s is m over s. So Higgs s output is transfer function time input. The input is step with magnitude m. So now we get the Higgs s k over tau s plus 1 time m over s. So for this case, you can refer to the characteristic or dynamic behavior of the first order processes. Okay, then you can uh, go to dynamic behavior of first order processes.